Welcome to our presentation, Comparison of Dimension Reduction Techniques on Clustering Tasks. I will be talking about clustering and dimensionality reduction and how they are relevant to the subject we are focusing. Safa will be explaining the math part with some math added. Selçuk will show the experimental setup and results, and Mustafa will talk on some possible improvements and will conclude the presentation. What is clustering? Cluster analysis is the task of grouping a set of objects in such a way that objects in the same group are more similar to each other than those in other groups. It is a main task of exploratory data analysis and a common technique for statistical data analysis, used in many fields including pattern recognition, information retrieval, machine learning, and etc. Here are the most used clustering algorithms: k-means, mean shift, dbScan, EM with GAM, and agglomerative hierarchical clustering. What is dimensionality reduction? Dimensionality reduction is the transformation of data from a high-dimensional space into a low-dimensional space so that the low-dimensional representation retains some meaningful properties of the original data. Working in high-dimensional spaces can be undesirable for many reasons. Raw data are often sparse as a consequence of the curse of dimensionality, and analyzing the data is usually computationally intractable. Dimensionality reduction is common in fields that deal with large number of observations, such as signal processing, speech recognition, neuroinformatics, and etc. And here are the most used dimensionality reduction algorithms: PCA, NMF, kernel PCA, LDA, and autoencoders. K-means clustering is a method of vector quantization originally from signal processing that aims to partition n observations into k clusters in which each observation belongs to the cluster with the nearest mean, serving as a prototype of the cluster. This results in a partitioning of the data space into Voronoi cells. We can see it on the right. The problem is computationally difficult, NP hard. However, efficient heuristic algorithms converge quickly to a local optimum. Hence, it is a useful tool to use in unsupervised problems. The principal components of a collection of points in a real coordinate space are a sequence of unit vectors where the ith vector is the direction of a line that best fits the data while being orthogonal to the first I-1 vectors. Here, a best fitting line is defined as one that minimizes the average squared distance from the points to the line. These directions constitute an orthonormal basis in which different individual dimensions of the data are linearly uncorrelated. Principal component analysis, in other words PCA, is the process of computing the principal components and using them to perform a change of basis on the data, sometimes using only the first few principal components and ignoring the rest. Now, we will explore some examples of k-means clustering, some usages of k-means clustering. In image classification problem, we have to classify a given set of images into a given number of categories. Training data is available in classification problem, but what to do when there is no training data available? To solve this problem, we can use clustering to group similar images together. Clustering is an unsupervised machine learning where we group similar features together. It interprets the input data and finds natural groups or clusters in feature space. The example on the left uses transfer learning model to extract features from images, then uses these features for clustering. In that example, k equals 2, k-means used is because there are only two classes. This can be used for labeling where we don't know about the classes of the images, as manual labeling will be a challenge. On the right dataset, the MINIS dataset, the accuracy score increases with the number of clusters. When the number of clusters are equal to number of classes, the accuracy is around 55. The accuracy is highest for 256 clusters, which is around 90%. We can ask, why do we need 256 clusters when there are only 10 digits? This is because there can be multiple ways to write a particular number. Principal component analysis (PCA) is a widely used statistical technique for unsupervised dimension reduction, and K-means clustering is a commonly used data clustering for unsupervised learning tasks. To find the relation between K-means and PCA, the paper proved that the principal components are the continuous solutions to the discrete cluster membership indicators for K-means clustering. Equivalently, they showed that the subspace spanned by the cluster centroids are given by spectral expansion of the data covariance matrix truncated at k-1 terms. These results indicate that, according to them, unsupervised dimension reduction is closely related to the unsupervised learning problem. That's why we wanted to focus on K-means and PCA together. Also, we wanted to check the literature on dimensionality reduction for K-means clustering and found a paper, Randomized Dimensionality Reduction for K-means clustering. The common dimensionality reduction approaches for K-means clustering are in this paper is feature selection, a small subset R of the actual D features from the data are selected, and feature extraction, a small set of R artificial features is constructed for each D-dimensional data sample. We can see the examples, algorithms that they used in feature selection and feature extraction. There is a paper, this is the paper, which discusses the evolution of the presented methods, but they don't discuss the implementation aspects of these algorithms. In this project, we tried to implement some of our own suggested methods and compared them to PCA.
Now I will talk about the mathematical background of our project. First, I'll talk about our clustering method, which is the K-means algorithm. In K-means algorithm, we are trying to divide our data into the cluster by using this rule. Each data point is assigned to a cluster where the distance between the data point and the cluster mean is the minimum among all the clusters. And the cluster means are computed as a solution to the optimization problem, which is the sum of all clusters and in all clusters, the distance between the data points and the cluster means. And when we take the derivative of this error function with respect to the cluster means, we can find the solution. An important thing to decide is the number of clusters. How do we know we are separated well enough is given by the distance formula between each clusters. In these examples, you can see that the data here is easily separated by two clusters, but not so much here. This is more ambiguous, so we need to increase our K here. Now I will talk about our dimensionality reduction methods. First one is the principal component analysis. Here our goal is to find a subspace where we can represent our data in D prime dimensions instead of D dimensions. And we define a reconstruction error, which is the sum of differences between the reconstructed data and the original data. And reconstructed data is given by Y times E. These E's are the basis of our D prime subspaces. And we can say that this error is minimized when the E's are the D prime eigenvectors of the scatter matrix. And Y values are called the principal components. When we sort the eigenvalues in the descending order and select the corresponding eigenvectors, we find that most variant dimension is the first one, and so on, so that we can select the number of dimensions by looking at the eigenvectors. The second method to reduce dimensionality is the Gaussian random projection. First, we start by defining a high-dimensional Gaussian with the probability density function. Then we compute the expected squared norm of a random chosen data point, which is given by n times sigma square. Then we show that the distribution of these expected squared norms are concentrated around its expected value by using this inequality. Then we say that counterintuitively, that for a large enough n, our distribution lies entirely on a thin shell with the radius of sigma times square root of n. And after defining our radius, we define our separation. We say that the two Gaussians are C-separated if their means are C times radius apart. And then we say that the mixture of Gaussians is separated if the all Gaussians are in this mixture are pairwise C separated. And after defining our separation, we say that when we pick a D prime Gaussians among D Gaussians, our C prime new D will be C times square root of 1 minus epsilon with the probability greater than 1 minus delta if we select our D prime according to the following rule. Here, epsilon and delta are some accuracy parameters, and the C1 is a constant. After defining our D prime, we say that we can project the data with D Gaussians to a subspace of dimension log D. So this is the greatest our advantage of Gaussian random projection. And another advantage is that when the first data is skewed, not spherical enough, we can say we can represent our data with the spherical Gaussians, which is very easy to compute.
I will talk about our experiment and the results. First, let's talk about the configuration parameters of the experiment and how we chose them. Here, n is the number of images. COCO dataset has more than 100,000 images, but we took some subset of different sizes to see the effect of the sample size. D is the dimension of the data in the original space. In this problem, it corresponds to the number of pixels times 3 because of the RGB channels. Images in the dataset have varying width and height values, but we made it consistent for all images by resizing them. After resizing, we flattened the images to get one-dimensional vectors. For example, if we resize the images to 64 by 64 pixels, that means D equals 64 times 64 times 3. dPCA and dRP are the dimensions in the reduced space of PCA and random projection methods. We set dPCA constant and experimented on the dRP value to compare their errors and time performance. And lastly, we have K, which controls the number of clusters in the K-means algorithm. In the K-means algorithm, there is no best K parameter. It is open to interpretation and depends on the dataset. Usually, people use elbow method to decide on this parameter. The elbow method runs K-means clustering on the dataset for different K values. And then, for each value of K, it computes an average score for all clusters. Here, that score is the sum of square distances from each point to its assigned centroid. In this plot, x-axis shows the value of K, and y-axis is our cluster score. As you can see, curve looks like an elbow. The score decreases steeply at first, and then starts decreasing slowly. That transition point seems to be around 20, so we chose 20 as the total number of clusters. On the screen, you can see the parameters we have tried. We tried 5 different image sizes and 4 different total number of images. Also, reduced dimension parameters for the random projection method are shown on the screen, which is dRP. When we consider all possible combinations, it is more than 100, so it takes a considerable amount of time. And because we have taken time measurements, other processes may sometimes intervene, and as a result, we might get inaccurate results. That's one problem. Also, these algorithms require a lot of memory. PCA needs to calculate the correlation matrix for the features, and it requires a D by D matrix. For example, in 128 by 128 dimensions, PCA requires around 8 gigabytes of memory. So it is already at the limit of our personal computers. So instead, we used a powerful workstation to solve both issues. But still, we couldn't get the results for the largest case. We run k-means on both PCA output and random projection output. We compared them in terms of error and elapsed time. Here, our error metric is the mean Euclidean distance to centroid. Of course, the dimension of centroid depends on the reduced dimension. We don't want that because methods may use different number of reduced dimensions. So we calculated the centroid in the original dimension first, and then calculated the distance values in this original space. We used the same scikit-learn package for both methods to make the comparison fair. Now I'm going to give the results. Of course, I'm not going to show the results of all these combinations due to the time constraints, but we shared our results in the reference document if someone is interested in other results. Here is the result for 10,000 images with 64 pixel height. The plot may look a bit complicated at first glance, so let me explain it. Here, x-axis shows the dimension reduced by the random projection method. And we have two y-axes. Blue numbers show the error, and orange numbers show the time. The elapsed time is computed as the sum of projection and clustering time together. Solid lines on the plot are the result of the random projection method, and the dashed lines are the result of the PCA. Since we fix the dimension of PCA, we see only horizontal lines for PCA here. So x-axis applies only for random projection method. As expected, elapsed time increases as the dimension increases, and generally the error decreases with the increasing number of dimensions. But it's not always true. You can see some zigzag patterns here. That's because of the randomness factor of the method. To mitigate such anomalies, we run the algorithm 5 times and report the average time. But still, we see some irregularities as shown on the plot. For this configuration, we can say that PCA is better. Even for the large dimensions, random projection cannot reach error levels of PCA. Of course, at 800 dimension, we see very good results from random projection, but as I said before, we consider that point as an irregularity. Let's increase the original dimension and see if something changes. Here, the height of the images is increased to 128. There are two important points in this plot. First, let's look at the point where blue lines intersect, right here. That point is the place where the errors of the two methods are the same. When we compare time values at that point, we can see that PCA requires more time than random projection. So random projection is better. Similarly, let's look at where orange lines intersect. Here. At that point, execution times are the same. When we compare error values at that point, PCA error is larger. So it means that if we give the same time to both methods, random projection gives better results. So for this configuration, we can say that random projection is clearly better. At this point, we may think that increasing the dimension will favor the random projection method even more. However, that is not the case. Let's move to the next result. Here, we increase the dimension again, but as you can see, PCA is better. Random projection error doesn't even reach the PCA error levels. That may seem counterintuitive at first, but when we think about it, it really becomes very difficult for random projection to preserve the same amount of information when we increase the original dimension. PCA, on the other hand, PCA looks at the data, it analyzes the data. So even though increasing the dimension increases the required execution time for the PCA, it can still capture patterns in high dimensions. Next, we increase our sample size, which is the number of images. We increase the sample size from 10,000 to 20,000. As you can see, there are small differences, but overall the plots are very similar. Let's increase it even more. Again, plots are similar, so we don't see any significant effect of the sample size on this comparison. Now I would like to show some clusters. On the left, you can see some images from the POCA dataset. We picked 9 images from different clusters and shuffled them. On the right, you can see the images belonging to the same clusters in 3 by 3 grids. You can see that similar colored images are clustered together. In the center, we can see images with white and blue colors. On the lower left, we see greenish colors. The algorithm clusters according to the colors only. It doesn't understand what is inside the images. But we observe that some clusters also make sense semantically. For example, on the left cluster, we see mostly food and plate images. So K-means somehow captures that information as well. Let's move on. Again, here we see similar images in the same clusters. Here, for example, most of the images are snowy images. Let's show one more clustering. Again, similar images are clustered together.
So in order to put a different perspective on these projection ideas, we thought of this Fourier-based kernel trick that we kind of also discussed in the class to some extent, and also to see what can it give in terms of timings and accuracy. So to this end, we introduced a map which is the projector from little d to capital D. It is based on the kernel trick that we also discussed in class. This K here is kind of a similarity measure. X and X quote are 2 different samples of, for example, images. If the images are kind of too similar to each other, very similar images, this K is supposed to give some low metric, 0 kind of things. And if the contrast between 2 images are getting higher, so should the kernel's value it gives. So this kernel trick is very useful and all that, but it's kind of computationally expensive because you need to do these things for maybe the dimension you are having this kernel is very, very high, or the pairwise computations may be too much. So in order to overcome this, people have come up with this idea of approximation, another layer of approximation with a dot product. Here is Z. Not every kernel is amenable to this kind of approximation, but if it complies with kind of Mercer's condition and stuff, you can come up with some kernel and Z pairs. And here we use Fourier bases, the cosine transformation basically, not the sine one. We ignore the sine components from the theory. So the usual projection we use in the Gaussian case, for example, is a matrix multiplication directly, but this also includes a cosine component, so you have a rotation in the process. Where does the randomization come? It comes from the random variables that are W and V. We sample W from the Fourier transformation of the kernel we theoretically trying to approximate, which is the Gaussian kernel here. We used RBF kernel. And the Fourier transform of the Gaussian signal is also Gaussian, so it conforms to probability distribution properties, so we can safely sample from it. And B is a uniform from the from the circle, minus 2 pi to 2 pi. So in a pictorial words, it's kind of this first project, W and B, the usual stuff, but also rotating. So this is the kind of main difference between Fourier-based, this kind of transformation, and the usual Gaussian one. So the random Fourier features, the algorithm is actually not so complicated after you do these samplings, after you decide what channel to approximate, what hyperparameters to tune, the gamma thing, the new dimension, etc. You can easily find, you can easily compute the new dimension, new projected image. So as I said, we use the Gaussian kernel for this, and the theory says if you were to test a new image under these transformations, by testing, I mean you, for example, you put some linear classifier or something on top of these projections, and in the test time, all of a sudden, instead of kernel shrinking, if you use this, the ND versus D plus D appears, which is a kind of very considerable amount of improvement. So we kind of expected this time improvement, and we see that here. The green one is the Fourier-based transformation, and it outperforms both of the transformations in almost practically all of the new dimension sizes. For example, towards the end, PCA goes after minutes and minutes, maybe 3 minutes, but the Fourier-based one is under 25 seconds, almost 8 times better timings, even though we scaled, the COCO data set has varying sizes of images. So for conformity, we size the images to 64 to 64, and this is kind of the baseline for all of these so that we can compare them. So timing is very well, but unfortunately the accuracy, so to speak, didn't turn out so good. Kind of on average 20% worse than PCA. The metric I'm talking about is, as my friends discussed, error calculation thing. So there might be a reason about this. Might be this is because images are kind of translation variant, and with these rotation things, you hinder the ability of what comes after it to some extent, because as humans we are fine with rotating images because we can rotate our heads also and see that it is the same image, but computer it is kind of different. For example, if you have a neural network well trained on an MNIST dataset, but the second you kind of rotate the digit, it doesn't know what to do. So we ponder this might be the reason for not so good accuracy. And in conclusion, effect of some randomized projections are examined on a practical data set to to kind of evaluate the overarching theme of randomization in this class. K-means was a helper tool in assessing that metric. Main comparison was about Gaussian and PCA, and as my friends mentioned, for some dimensions, the randomized projection wins over the PCA, and it is kind of indifferent to the sample size. Either you use 20K samples or more, for example 30K, but PCA, so PCA is the Gaussian transformation, the randomized one. There are some cases it is better than the PCA for both timings and the accuracy. So it is choosable in that way. And lastly, as I mentioned, we looked at some Fourier-based projections, but timings were good, and all that, but unfortunately the accuracy didn't turn out so good. Might be because of this translation sensitive nature of the images, maybe that. So that was the end of it. Thank you for listening.